Hi, this lesson is on the 4.1, 4.4 exploration of polynomials. So after completing this exploration and watching this video, you should be able to identify key characteristics of polynomial functions, sketch polynomials given certain characteristics, write polynomial equations given a graph, write polynomial equations given characteristics. So this worksheet starts with a review of parent functions. So if remember, the linear parent function is just the line y equals x. Quadratic, we have x squared. And then these are the new ones. Cubic, read that one. Cubic x to the third, right? And then with that inflection point at 0. And quartic is x to the fourth with those repeated zeros hitting the x-axis. Okay, then if we think, remember domain is the x values. So the domain of a linear function, the x values, negative infinity to infinity. This is x squared. So again, negative infinity to infinity. Same thing, negative infinity to infinity. And here we also see negative infinity to infinity. So for the domain, remember those are what x values is our graph going to touch. And as we can see, all of these graphs go forever, both left and right. Range is our what y values are we going to hit. So linear, this line is going to hit all of the y values as well. So that is negative infinity to infinity. Quadratic, we see we will not hit any y values below the x-axis with the parent function. So 0 to infinity. And now if we look at the graph, we see that it is touching 0. So it does include 0 in our range. So that's going to be a bracket. Cubic, we see it goes forever down and it goes forever up. So that is negative infinity to infinity. And quartic, much like the quadratic, it hits 0. So we're going to include that. And it goes up forever. So what we should notice here is that this is x squared, x to the fourth, x cubed, and just x. So x to the first. All of our even function is going to be 0 to infinity. All of our odd functions are negative infinity to infinity. So the degree of a linear function is 1. Quadratic, it's 2. Cubic, it's 3. Quartic, it's 4. Remember, the degree is that highest power. So I did write those up there in the power of those parent functions. Maximum number of solutions or zeros. So how many times is this linear graph going to cross the x-axis? Just once. This quadratic, it's going to be 2. Cubic is 3. And quartic is 4. Remember that zeros or solutions, the maximum number they can have is whatever degree that is. So now we're looking at turns and turning points. So how many turning points does a line have? 0, right? It doesn't change direction at all. Quadratic, we see it has 1 turning point, right? It's right there. It changes direction. A cubic function has 2. So if this, we could have something like that. That would still be cubic. Here we see 2. That inflection point counts for 2. And then quartic, we see 1, 2, 3 turning points, that is. So notice that the turning points is 1 less than the degree. And behavior, if the leading coefficient is positive. So all of these parent functions have a positive leading coefficient, so we can go ahead and analyze the parent function and behavior. So as x goes to negative infinity, we see f of x goes to negative infinity, and as it goes to infinity, it goes to infinity. Quadratic, remember, even functions are going to have the same end behavior, both pointed up. And then cubic, odd degree, so it's going to be opposite. As x goes to negative infinity, r of x goes to negative infinity, and as x goes to positive infinity, it also goes to positive infinity. And similarly, quartic would be the same end behavior as quadratic. Now, what if that leading coefficient is negative? Well, then all of our end behavior is going to change, right? So a linear negative would be a line going that way. So as it goes to negative infinity, it's going up. And as it's going to positive infinity, it's headed down. Same thing for a quartic. So a negative leading coefficient is going to be a open down parabola, which then both ends are heading towards negative infinity. Cubic is going to start up and down. So again, our end behavior just flips. And then quartic would look something like this. Both headed towards negative infinity. So now we're asked to sketch the basic shape, then place the x and y axes to illustrate indicated number of zeros. Enter a sample equation for each sketch. Okay, so first this would be our linear, quadratic, cubic, quartic. You guys see that on yours. I just couldn't fit it all in one page. So is it possible for a linear function to have no real zeros? For a linear, or in other words, for a linear function to never cross the x-axis? That is not possible. A linear function is always going to cross the x-axis. Now we think about quadratic. Is it possible for a parabola to never cross the x-axis? This is our parabola. It totally is, as long as we move it up one. So an equation could be f of x equals x squared plus 1. That moves it up 1, and therefore will never cross the x-axis. Why is it impossible to have no zeros on a cubic function? For the same reason as on linear, it will always cross the x-axis. Its domain is negative infinity to infinity, so it's going to hit all y values. And how about for a quartic function? We know that looks like this. And same reason as, or same idea as a quadratic. If we just move that up 1, we can write f of x equals, this is x to the 4th plus 1, right? Move it up 1, and then since both ends are going up forever, it will never cross. So how about a linear to have one real solution or cross the x-axis once, right? The parent function does that, so we can just write f of x equals x. How about a quadratic? Is it possible for a quadratic to only cross the x-axis or have one real zero? Not possible, because a quadratic will always have two answers, right? How about a cubic? Absolutely. There it crosses the x-axis once, right? Just the parent function. And why is it impossible to have only one real zero with a quartic? Same reason as a quadratic. It would have a minimum number of 2. So in a quartic, it can only have zero, 2, or 4 zeros or solutions. Now we move on to why is it impossible to have more than one zero in a linear function? So in other words, why can a linear function never have any more than 1 0? Because it only crosses the x-axis once. Or if we look back here, maximum number of solutions, 1. So that's also a reason. Okay, sketch a graph of a quadratic function that has exactly 2 zeros. We know a quadratic looks like this. Well, what if we just move it down one? Has exactly 2 zeros, right? Or so does our parent function. It's just one example. There's many. How about a cubic have exactly 2 zeros? Not possible. Because a cubic is either going to have 0, 1, or 3. And for a quartic to have exactly 2 real zeros, it's only going to cross the x-axis twice. So that's going to look something like this. And you're like, well, how do I figure that out? This means we have 2 real solutions and 2 imaginary solutions. So we can go ahead and write this in intercept form, and the intercepts don't really matter. The ones I'm just going to use are negative 4, so x plus 4, negative 3, so x plus 3, and then I have 2 imaginary solutions, so I'm going to write x minus 1 squared. Because if we had to solve this, right, we'd set this equal to 0 and take this yeah, never mind. But anyways, x minus 1 squared. Go ahead and graph that, and you'll on Desmos, and you'll find that that is a solution. I'm just going to move it up 1 because if, like I said, if we had to solve this, we would be taking x minus 1 squared and taking the square root of a negative number here, which would give us imaginary solutions, plus or minus there, right? Okay, now why is it impossible to have more than 2 zeros on a quadratic function? Because the max number of solutions we said earlier is 2. Exactly 3 real zeros on a cubic. We know cubic could look something like that. And there we have 1, 2, 3 real zeros. And really, like I said, any x-intercept would be just fine. I'm going to go ahead and use x plus 2, x plus 1, and x minus 2, which would make our x-intercepts negative 2, negative 1, and positive 2. Now, is it possible for a quartic to have exactly 3 real zeros? No, it has to be even. And then exactly 4 real zeros? Absolutely. Something like that. 1, 2, 3, 4. And again, any example here would work. I'm just giving an example. So okay, now sketch an example of the following types of functions. So a quadratic function with domain negative infinity to infinity and a range 3 to infinity. So we know domain is a given, right, with quadratic. Negative infinity to infinity is going to go forever in both directions, but our range, the lowest it touches is 3. So that means 1, 2, 3, that's where the lowest point or the min of our parabola touches. Quartic function, so 4th degree with domain negative infinity to infinity and range negative infinity to 2. So the lowest it goes, negative infinity, right? So we know it's opening down, and then the highest it goes is 2. So I'm going to go ahead and draw a quartic function. Then this point right here would be at 2. So I'll draw my x-axis, something like that, right? The highest that point touches is 2. Now, a cubic function, so 3rd degree, that increases to x equals negative 3, then decreases to x equals 4, then finishes in an increase. So I'm going to go ahead and draw an x-axis at x equals, we'll say that's negative 3, and then here is x equals 4. So it's increasing to negative 3. So until -3, and then decreases until x equals 4. And then it starts to increase again. It won't be that sharp of a turn. So something like that. So at this point is when we have that turning point and it starts to increase. Okay? So these are at x equals. That doesn't mean it has to touch, but simply change direction at that point. Okay, so now we're given this graph here, and we are told to answer each of the following a through j. So what's the minimum degree of this polynomial? We know we can find the degree from how many x-intercepts there are, and we see 1, 2, 3, 4. So we know it's at least a 4th degree polynomial, which means we have 1, 2, 3 turning points, right? The turning point is always going to be one less than the degree. Now we can go ahead and state our zeros. X equals, looks like -6, -4, 1, and 2. As x goes to -infinity, we see our graph is going towards infinity, as well as x goes to infinity, our graph is also going towards infinity. The domain, -infinity to infinity, right? It's going forever, both left and right. Our range here, we have to look at our lowest y value. What's the lowest this graph touches? Here, it gives us that point. So -4.298. And now that should be a bracket, right? Because it touches that point. And we go all the way until infinity. So these are G through J are some new concepts for us. Relative max means a maximum in that area. So if we look at the max, our relative max would be this point here, because in this area, the highest point is that vertex, okay? So turning points are where we're going to see relative max and mins. So relative max is this point, -1.641, comma 9.88. Okay, now using that same concept, turning points are relative minimum. Here's a relative min, and here's a relative min. So we have two of them. So -5.148, -4.298, and 1.539, -1.03. Okay, so now where's our graph increasing? Here we have decrease, here we have increase. Okay, so from here we're looking at the x values, -5.148 to -1.641. And our other interval of increase is right here, 1.539 to infinity. Now we want to connect those with, this is called a union symbol. Okay, so it just tells us that both of those are increasing. It includes both of those points. Intervals of decreasing, I see my graph is decreasing right here, as well as here, right? So this is -infinity to -5.148. Again, the union, -1.641 to 1.539. Okay, sketch the graph, state the degree. So this I know is second degree, and my x-intercepts are at x equals 2 and -1. So this is just a parabola with intercepts at -2. Oh, I'm sorry, this should be -1 and 2. Right, something like that. Here I know this is third degree, right, 2, and that's a 1 on there. My x-intercepts are x equals. Set this equal to 0, I get x equals 0. X plus 1 equals 0, x plus 1 equals 0. I get x equals -1, x equals -1. So I have 0, and then -1 repeats twice. That'd be -1. Okay, so what happens at a repeated 0? A turning point. And this is an odd degree, so we know it's going to end going up, and then, which means it's going to start going down. So this graph will look something like that. Okay, here we have a fourth degree with x-intercepts at x equals 0, and then that 3 is going to repeat 3 times. So there's my 0, here would be 3. And since it's an even degree function, both ends are going to end going up. And then we know we are going to go through the point 0, and then we have an inflection point there at x equals 3, so something like that. Okay, what degree here? We have 2, 3, 4th degree. And our x-intercepts are at x equals -2, 1, and then we have a repeated 0 at 3. Now it's an even degree and it's negative, so both are going to be down. We go through 2, go through 1, and then a repeated 0 at x equals 3. There's that. This is a 5th degree. 3 plus 2 gives me 5. Okay, my x-intercepts are at x equals 2, 2, -3, -3, -3. Okay, so I have -3 and +2. Okay, so this is negative and odd. So I know it's going to end going down. And my end behavior is going to be opposite since it's odd. So at 3, I have an at -3, I have an inflection point because it repeats 3 times. And at 2, I have a repeated 0, so a turning point at the x-axis. That should touch there. There. Degree here is 4. And our x-intercepts are x equals -2 repeated twice and +2 repeated twice. So at both, I'm going to have turning points, and since it's positive, both will be up. There we go. All right, 2 more here. This is a 6th degree, and we have x equals 0 repeated 3 times, and x equals 4 repeated 3 times. Okay, so I'm going to have an inflection point at each. Since it's even, they're going to be going in the end behavior will be in the same direction, and positive means they're both headed upward. So I have an inflection point at 0, and then another inflection point at x equals 4. Number 11, the degree, 1, 2, 3, 4, 5. And my x-intercepts are x equals 0, -2, 1, 3, -4. Okay. So I have 0, -2, -4, 1, and 3. And this is odd, so they're going to be, end behavior will be opposite and positive, so it'll end going up, which means starting downward, and then we just have one, I missed 0 there. And that's at 1. Sorry, that got a little messy. Okay. And then number 12, write a possible equation for each polynomial function. Well, this will be 1, 2, 3, right? 3rd degree. So we have f of x equals, now what are my x-intercepts? -1, 2, 3. So I can do x plus 3. That gives me an x-intercept at x equals -3. I can do x minus 2 and x minus 5. And those came from my x-intercepts, okay? This one, I see I have a repeated 0 at -8, so I'm going to do x plus 8, and then since it repeats, I'm going to square it. And again, that happens at -1, so x plus 1 squared, and then we see just a single 0 at x equals 5. All right, write a possible equation for a function with the following characteristics: degree 3, double root at 4, and a root at -3. So a root and an x-intercept or a solution all mean the same thing. So we have a double root at 4. So I have x minus 4 and double root. So that 2 squared is going to give me that. And then at -3, so I have x plus 3. All right, degree 4, an inflection point. So that means it's going to repeat 3 times at 2, right? So x minus 2, and it repeats 3 times, so that means it's cubed. And a single root at 5, so x minus 5. All right. And then it said it was degree 4, so let's just double check. Cubed plus 1, perfect, 4. Degree 3, roots at, so here it's nice, we get 3 roots, no repeated, so we can simply do x minus 1/2, x minus 3/4, and x plus 1. Perfect. Okay, degree starting in quadrant 2 and ending in quadrant 4. So if we look at our xy coordinate plane here, this is quadrant 1, this is quadrant 2, 3, and 4. Okay, so it starts in quadrant 2, it starts here and ends in quadrant 4. Okay, so we know it's going to be odd degree, right? Which they already told us, 3. But an odd degree polynomial ending down is going to be negative, right? So we have f of x equals negative. And then roots at -2 and a double root at 3. So x minus 3. Okay. Now degree 4, starting, so now we're starting in quadrant 3, we're starting here, and ending in quadrant 4, ending here. So that means we're starting down and ending down, and degree 4, so it's going to be negative. Double roots at -10, so x plus 10 squared, and a double root at 10. Okay, that's all we have for today. If you have any questions, reach out as always, and we are happy to help.